I was texting. That's why I was late today. It's a good reason to be late for something. Sorry, guys. I was texting. That's why I'm late today. Tampa Station is here. What's up? What's up? Robert is here. What's up? Just brewed morning coffee. That's good. I did the same. Let me know if the music is at a good volume. It's at a very good volume for me. I am rocking my Certified SolidWorks Expert cup. Let's go. Certified SolidWorks Expert. We did it. We got there. This cup is from 2020, but I got mine a little bit before that. Just a little bit before that. Guys, I ran into a real surprise when I was preparing for today's live stream. You know, we've been absolutely crushing it in the world of 3D CAD, in the world of SolidWorks, getting everything ready for this bass guitar. And, you know, we're basically now at the point where we're ready to start putting in these tuners, right? And so I was like, okay, this is going to be good. Let's start with our pictures. Let's take some pictures of these tuners. And so, you know, took a picture of the tuner assembly here. This is what we're going to put up in that headstock. Took a picture of the tuner assembly from the side. Took a picture of the tuner assembly looking down. Okay, that's good. Everything's good. I'm not worried. Everything is going great. And then I started taking the tuner apart. And just to kind of spoil the ending of this is what we ended up with. This is a lot of components that are part of this tuner here. We've got the housing, which is going to be our main part. We've got the tuning post, which goes down into this pinion gear and into this screw at the bottom. But this was not easy to take apart. These things, it required a lot of hammering and a lot of, basically everything is assembled in a way that it's really not meant to be taken apart after it is assembled. So there's a little cover on the bottom. This cover here, this 609 gear cover is on the bottom. There's this screw that goes through this pinion gear, which goes through this, but then you've also got the worm gear shaft. And I basically had to hammer that worm gear shaft out because once it's in there and engaged, you know, it's really not meant to come apart. I guess maybe what I did things in the wrong order. I took the worm gear shaft out before I took the pinion gear. I'll bet if I would have taken the pinion gear out first, I would have been in better shape. But the catch there is that this gear cover was on in a way that the only way I could really get it off was if I entered through the hole that's on the side here for the worm gear shaft. So a lot of parts. We got a lot of parts to create today and a lot of cool geometry that we're going to create today as well. You know, we've got this kind of like lofted, swoopy, lofty shape going on here that we get to create. We get to create this housing, which looks pretty easy from this view, but it does have some kind of cool curvature, some cool geometry to it, some cool curvature on the back side of this housing as well. And of course, the pinion gear and the worm drive shaft are going to be pretty fun to create. Now, Jeremy Rignerez has some terrific content on gear creation, both this pinion gear and the worm gear type of creation, where he really gets into the math that's involved. I'm not going to go that deep with this example. I'm just going to get these things looking good. And then I am going to go in and create the mate that allows the gears to spin correctly. So I'll create the gear mate so that when we turn the button over here, the worm gear drive shaft or the worm drive shaft will turn, and then the pinion gear will turn, and ultimately that will cause the tuning post to turn. So we will put in all of the mates for this thing. We'll make this a flexible sub-assembly when we put it into our higher level assembly. So in the higher level assembly, we'll actually be able to turn those tuners and see what happens. But yeah, I was a little bit surprised when I started taking this thing apart as to how many components were in here. And so I thought that a good strategy would be to go through and to take pictures of as much as I could. So I took a picture of the assembly. I took a picture of the button from the end. And this is another technique that I'll use sometimes. I went into my photo editing software and I actually traced the outside perimeter because it's hard to see where the deviation is when you're in SolidWorks, and when you take this image and you make it transparent, it's a lot easier to see when you're in your photo editor. So in the photo editor, I just sketched some splines, kind of giving me the basic boundary for that swept and loft geometry. Took an image here from the side, took an image of that screw. So took some pictures along the way as I was dismantling this thing. So after I took the button off, you can see that I'm just left with this is the worm gear shaft here going right into the housing. So everything is still engaged. And then what I ended up doing was taking a hammer here and just hammering this thing. I don't know why I drew the hammer like that. This is the handle of the hammer here. So I just took this thing and just hammered it, bang, 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 just hammered it through and got it to disengage. But, you know, I think that in hindsight, what I could have done is taken off the back panel of this thing and popped off that back cover first. And that probably would have been a more elegant solution. So I took a picture of each of the components here. We'll use these pictures as we go through and do the design. I'll add all these pictures to the IMGUR so that if you want to do this yourself at some point in the future, you will be able to. I haven't added those pictures yet, but I will do so at some point in the near future. This gear is missing a tooth. That was missing when I took the... Let's see here. That was missing when I took the cover off. You know, I might have done that. I might have banged that out when I was hammering on that thing. So that might have been my fault that is missing. I'm trying to think if that was off already, but I don't think I had vision on that thing until I took the worm drive out. So I might have, when I was hammering on it, I might have broken off that tooth. But this is why sometimes if you're ever tuning a guitar and like it seems like the tuner just slips at one point, that's why you may have broken off one of the gears on that pinion gear. There's a nice view of that worm gear shaft. It took, you know, 2 different pictures of it. One from kind of the one side. This one here actually shows you the, you know, the notch, the key in that worm gear shaft. So I like that picture. We're definitely going to end up using that one. So we got our work cut out for us. I did lay out the geometry down here. I've got it. It's a little bit off camera, but I did lay out basically what you saw in that overall image. That's what I've got laid out here next to me so that I can continue to stay on track as we go through today. So I basically have this whole thing that you see on the screen here. All the stuff you see on the screen over there. I've got it down here next to me. Can't see my fingers. I got it down there next to me. So I'll be able just to reach over, pick up the parts, start measuring them, start modeling them, going on to the next, to the next, to the next. So this is what we're going to do today. Let's see here. There is a... So this is a 3-string bass now. Yeah. You know, this is a pretty some of this geometry is pretty complicated design, Robert, and I think that's why it becomes so standard. Like this shape here, when I was looking at it, I'm trying to think about how I'm going to model this. Like I'm going to end up using some surfacing to model this thing up. I don't really know how I'm going to do it. I haven't done it before. So we're going to be watching that live today. I'll be thinking through how to create this geometry. But what I realized in taking this apart and looking at it is that this is pretty complicated geometry, and so I've bought several basses in my life that have this same exact tuner shape on them, and so, you know, over time I've accumulated some of these that have maybe broken, or I bought some cheap, you know, like knockoff copies of this thing. So I just ended up taking one of those cheap knockoff copies. I busted open the bag. This was the bag that it came in. I just busted open the bag, so it was new, and then I just started breaking it apart. And, you know, ended up with this exploded assembly view. So I still have the 4 original tuners for this thing still in the case where I took everything apart. But I also have the sacrificial one, which I was hoping I had an old one. I think, you know, I've had ones that the tuning has stopped working correctly, and so I've ended up replacing them. I was hoping I had one of those in my guitar repair case, but I guess I just tossed it because I was like, it's not working anymore. I don't want to get confused with a good one. So I just ended up tossing it out. And Tampa Station says, big day coming up in the cat office. I don't know if you're referring to something that's happening at your office or if you're just referring to this mess that we're looking at here today. But for me, this is a big day. This is going to be a lot of work to get through. We're going to get as far as we can today. This might spill over into next week. We'll see what happens. Ideally, we will get it all done today. So let's not waste any more time with the intro. Be sure to like, be sure to subscribe, be sure to buy a TooTallToby t-shirt, the softest material in the world. What's up, Brad? How you doing? Welcome, welcome. We are very excited to have you in here today. Thank you for joining us. Don't forget, buy a t-shirt. Buy the softest t-shirt in the world. You can wear it to upcoming, you know, any kind of upcoming technical event, conference, live stream, whatever it is you're doing. A great way to represent. And of course, be sure to like, be sure to subscribe. And let's get into it today. We're going to try and create these 13 parts today. It's going to be a speed run. Let's jump over to our keyboard and mouse cam, let's move this plan over to the side here so that I can keep track of our numbers. And let's go, let's go, let's go. So today we are going to be working on this bass guitar. Whoops, let me just set up one thing on my screen here, make sure that I've got what I'm expecting from my data management here. Okay, good deal. So, you know, do we need to design anything in do we need to design anything in context with this? The only thing that we would really even consider designing in context would be the location of the pilot hole that goes on the neck here. That's the only real interface that's happening. I mean, maybe you could say the diameter of the bushing and the diameter of this hole here should also be linked. So if the diameter of the hole changes, the diameter of the bushing changes. But we're dealing with a bunch of purchased parts here, so I don't think we need to go that far. I think we can just make this whole assembly here standalone. So that's what we're going to do. We're going to start with the 601 housing. We're going to create the housing, then we're going to create the assembly from the housing. But we're just going to make all the parts standalone and assemble them. So this is going to be what we would call a bottom-up assembly design process. We're going to start with one component, the housing, which everything kind of sits in. And then we're going to use that component in the rest of our design. So this is the housing here. I like this when I can get both views here on the camera at the same time. So this is the housing here. We do have some pictures of the housing, which we're going to use in our design process, but we're also going to be just taking some basic measurements and using those measurements to help us drive the size of this thing. I'm going to draw this in a view. Wait, hold on a second. I forget something. Just trying to find out where the head points down. So when we're looking at this thing at the back of the neck, this little triangular shape that's sticking down with the mounting hole points down. There's a little triangular shape there that points down. So that means that this one that I'm drawing up is going to go up the what would be the left side if we're looking at it from this view here. The left side with that little triangle pointing down. So that's good. That's good to know. The triangle is pointing down on the neck. So when we create this thing, that'll help us understand that the top view is going to look like this. I just want to make sure I'm very clear on what I'm saying here, guys. This part has a little triangle at the bottom here, the very bottom of the part, and that triangle mounts like this. There's the triangle shape. It goes up like this, and then there's one little hole here in the back of the bass guitar, a little pilot hole, that one little screw goes through to hold the orientation of the tuner. And then the tuner has a hex bushing, a threaded hex bushing, where on the top you use that hex to thread into the housing. So this housing has a threaded element to it as well, and between those two, it's able to hold the whole thing in place. So this looks like it's a cast part, possibly a machined part. It's kind of hard to tell, but I think it's probably cast. I don't know, maybe it is. I mean, there's certainly elements of it that are machined. It probably starts out cast and then they machine in the some of the additional elements. So, you know, let's get into it. Let's start modeling this thing up, and we're going to start out here by just taking some basic measurements. So the measurement of this thing is, oh, look at how we're starting out the day, 0.69. It came up right on the mark, 0.690. What a great start to the day. And then this on the back side here, it's going to go up to a tangency peak of 0.9125. So we'll go new, we'll make this a part in inches. We'll go top plane, begin a sketch, orient our view. We'll say that this is going to be a diameter here of 0.69, and you guys know that that makes me happy. And then we are going to go up to the top of that that circle up to the very top section here at the tangency point is going to be the 0.9125. Oh yeah, Brad said he just got himself a TooTallToby shirt. You are going to be happy with that, Brad. Congratulations. And you're going to now be able to wear the softest shirt in the world. Congratulations. And thank you. Thank you for the support. All right, and then from that max point of tangency to the tip of the triangle, 1.11. We are liking these numbers today. So I'm just going to create a line here that goes tangent, and there's going to be a little arc here. I don't know what that arc is yet. And then this is going to go tangent here as well. Oh, it picked it up. Perfect. And this is going to be vertical. And this is going to be from here to the arc, 1.11. And then that arc is going to have a radius of, I don't really know what it is yet, but I'm going to say it's going to be a radius of 0.1. Sounds good. Or sorry, 0.1. Okay. I'll take it. Okay, and make sure this is tangent here. And that's essentially our layout for the tuner. So this will be layout from top. And then we can save that. And that's going to get saved as RBG-601. So nice to have a plan for this thing. Tuner, housing, and right mouse button, sketch color. I'm going to be trying to go at a little bit of a faster clip today, guys, because of the amount of work that we're trying to accomplish. But if you need me to slow down, or if you want me to review anything that I did, just say the word and we'll go back and we'll review. All right, so I think, let's see here. This one looking down from the top is pretty clean. Here's a half assembly looking down from that. That's pretty clean right there. I think I'm going to just stick with that one. For this one, I was just kind of going through and essentially like eyeballing everything up. I wasn't really going too crazy with the orientation. I did align these when I was creating these sketches. I did align them to vertical horizontal, so it should be pretty close to vertical horizontal when we drop it in here to our assembly, or to our part, I should say. Okay, and then when you are able to size this correctly for width, but the height still looks incorrect, it could be that you're experiencing distortion because the angle at which you took the photo. So you do have the liberty to stretch this a little bit and see if things kind of fall more in line upon doing so. So that's basically what I'm doing here. Again, we use the images to help us with the layout, but not necessarily to define the geometry. We just kind of use the images to help us. That's the point of the images. Image from top. You can always do a double check, kind of like a sanity check of your measurements if you feel like things are still a little bit off. I'm still getting 1.11. It's actually 1.1185. I wonder if that would make a difference. 1.1185. Yeah, a little bit. Remember that your image is not dependent on anything. You don't have any feature dependencies on your image, so that gives you the freedom to interchange between your image and your layout in the tree. So you can get your image looking good, then you can move it up. Now you got your layout. Now you can edit your layout and then use your layout to or use your image essentially to drive the layout, for example, to get something like the location of this hole. So the hole is not exactly centered on that radius. You know, sometimes they are, sometimes they're not. Perfect. It's like exactly what I'm coming up with in the model is what it is, 0.0895. And we're going to make this vertical to the origin. We can see there's some distortion in the image. Okay, things aren't perfectly aligned. That's okay. We'll give ourselves a distance dimension here using that layout to drive the distance to that location. And we can also, at this point, create the layout geometry for this little sleeve that sticks out for what's ultimately going to be the tuner or the button. So now our angle, our angle for this, much easier to define when we've got our layout geometry being driven by the image, or maybe I should say guided by the image. So 0.286. Oh, a little bit of a... Oh, no. I measured that wrong. 0.306. So that looks pretty good there. You could always take this. Sometimes what I'll do is I'll take this and I'll mirror it and then kind of use that to help figure out approximately where this should be. So I'll kind of split the difference for the location relative to the image. Again, sanity check, always important. You know, you can use the image to help guide the design, but look at that, 0.552. I love it when these numbers are lining up with what I'm getting from the image. So now I can take this and I can just drag this and kind of like split the difference on the image. I did measure the image, so should be pretty close there. And then I can put in a final dimension to that center line, 0.216. Okay, I'm happy with that. That's a pretty good start for our layout. We could also, at this point while we're doing the layout, you know, anything I can see from this view, maybe it's worth it to include. So looks like 0.549 for our next diameter here, 0.549. That's kind of like the beginning of that sleeve. And then the ID for the sleeve looks to be about 0.429. And of course, it's going to be threaded. And then there's a smaller hole down at the bottom there, which I can get from the bottom, 0.259. And what we're looking at in this image is the peg is still in there. So that's why we're seeing that it looks a little different from like this view here where it's just the empty sleeve. But I've got the physical part here, so I'm able to measure to the physical part. That's going to, you know, really help out with the process. So, okay, I'm feeling pretty good about this. I'm thinking everything is looking good, feeling good. There is like a tiny little pocket in this thing. I'm not going to worry too much about that. It's only maybe like 3 thou deep. That just seems like extra geometry that I don't need to include at this point, especially since this is a purchased part. So at this point, I think I'm ready to start creating actual geometry. Top plane, begin a sketch. You know, as always, this is something we talk about a lot in TooTallToby and, you know, 3D modeling. You always got to decide what your starting plane, starting profile is going to be. And in this case, we got to decide where everything is going to be aligned. I think that in this part, what I'm going to do is utilize this plane right here, right across there. I'm going to utilize that as my top plane. So right where the machine head interfaces with the bass guitar, this surface here is going to press right up against the back of the neck of the headstock of the bass guitar. So I'm going to make that my top plane. So this is just something that it's always worth thinking about. You want to remember this is going to be the foundational part in the assembly, so that might play into your decision as well. Top plane, begin to sketch, orient the view, right mouse button, select chain. We'll also pick this and these 3 here and convert entities, and then we can... Actually, you know what? I don't think I want these extra entities here. Not yet. Not ready for them yet. We can either leave this and do contour selection, or we could trim it. S key extrude. Thank you. Let me start over. Here we go. Top plane, begin a sketch, orient our view, right mouse button, select chain, and we'll also pick this circle, convert entities, trim this guy here, S key extrude, and that's going to go to a depth of 0.3985. Reverse direction. Okay, that's our first feature. When we look at this feature from the from this side, we can see that there is some curvature on the back of this thing, but it's just a simple fillet. No real challenge there. We just need to measure what the radius of that fillet is. And there's also a taper on that back wall. So it may help to have a side view of the part, the physical part, or you could do your best to measure it. I'm going to just do my best to measure it. Right plane, begin a sketch, orient my view. What I'm referring to here is the location here. This comes down and then goes into a fillet of 0.25. The other reason it's nice to have this opportunity to show you this is that we can demonstrate the use of cut through all using essentially a surfacing type of a technique. So I'll show you what I mean by that. Drop it an angle here. It's not much of an angle. 6 degrees, that's fine. Taper may be casting draft. I think it's actually aesthetic because it's a different taper on the other side. But it could be you're right. I mean, I don't know for sure. I just think in this case it looks more like it's aesthetic. So now at this point, we've got an open sketch. We can S key extrude cut right mouse button through all both. And what this does is it essentially creates a surface cut. So we don't have to close off the sketch. We don't have to create that extra geometry. We can just create the sketch like so and give ourselves that geometry. And it's interesting, that location actually should correspond with this location here. So I might be able to even eliminate that angle and just take the center of that radius and make it vertical to this. Yep. Okay, cool. So just continuing to use the layout sketch to help drive our design. Sometimes in that spot, I'll sketch a center line so that my coworkers can see, oh, okay, I can see this is vertical to, you know, that point from another sketch. Sometimes I'll leave a note, you know, it just depends. Okay, so that gives us that second feature. Now for our third feature, we can create that revolve, and that revolve is going to be at this center point. So I can go top plane, hold control, and drag that top plane down, let go of control, pick that point, try it again, pick the top plane, hold control, drag the top plane down, let go of the top plane, let go of everything, click on that point, and then right mouse button. That gives us a plane for the revolve, plane for revolve. And then we can pick that face, begin a sketch, orient the view, hold control, select, 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 convert entities, we can trim, and we can single click on this line here to pre-select it for the revolve. We can do a revolve there. So this is kind of a cool example because we're showing that you can use a master model layout technique in a single part to get all your information down in one sketch, and then to use that sketch to drive the rest of the geometry throughout the remainder of that one single part. So even though it is one single part, we still have the ability to use master model layout to simplify the process and kind of speed up the overall process. Let's go top plane, begin a sketch, orient the view. We'll pick these guys here and this, convert entities, S key, trim, S key extrude, 0.0815. Getting very, very precise on this one. It's very important. This one's precise, right? Just kidding. It's not important at all. Okay, that gives us that little nub that's sticking out there. Top plane, begin a sketch, orient the view, and take this guy, and I don't know what the depth of that cut is, so I'm just going to take that guy and... Oh, wait a second. I missed a circle in my master model layout. So let's edit that sketch of the master model layout. There's the diameter of the main sleeve here is actually smaller than the diameter of the, so 0.551. Oh no, I do have that one in there. So that's the smaller one? Wow, that looks so... Just a little bit of an optical illusion, I guess. Just looks like it's there's way more of a gap, but you know what? It actually doesn't look that bad. 0.421. Select face, begin a sketch, orient the view, and we can continue to use our master model geometry. Convert entities, S key extrude cut, and that's going to go to a depth of probably about the same. 0.3835. So close. Okay, so now we look at the back side of this thing, select face, begin a sketch, orient the view, and on the back side of this thing, we have a diameter of 0.5575, which I think we can assume is the same as this one. I don't know, maybe I don't want to make that assumption. .5575 and extrude cut. This one's not threaded, that's why I'm saying maybe it is intentionally a little different. 0.37. Take a quick sanity check here. Look at this thing in a section view. That looks like a pretty good amount of wall thickness on either side. Okay, I'm happy with that. Select this face, begin a sketch, orient the view, convert entities, S key, extrude cut, right mouse button through all. Remember, if you can get that workflow down, you can save yourself a ton of time. Well, let's do it again. Select face, begin a sketch, orient the view. Select this guy here, convert entities, S key, extrude cut, right mouse button through all, right mouse button. Nice, quick, precise workflow that you can use over and over and over again. Okay, this hole, it looks like it's tapered. Could probably do this one as a revolve as well. Oh, this actually, you know what? This is stepped. Stepped and tapered, I'd be willing to bet. So, let's see what we got here. So 0.92 is the depth of this thing coming in from this side. I'll go back and get the dimension in a second. .277. And then I'm going to just click on this face here and do section view and then drag the section view up. I just kind of want to see what that's doing as far as taper goes. It's really hard to tell what's going on with the taper on that one. That one might actually just be straight. They might both be straight. I'm going to assume that they're both straight. 0.2045. Select face, begin a sketch, orient the view. 0.2045. S key, extrude cut. Right mouse button through all. Right mouse button. Let's look at that section view again. Yep, that's what it's doing. It's pretty cool. It even got this geometry here. When you're looking in, there's a little pocket you can see into the pocket where the, this is too big, this tool's too big. You can see into the pocket where that cut protrudes through, and it's basically exactly what we got here in the idealized model, in the virtual twin. Gearbox machining is detailed. Yes. All right, here we go. Let's hide this. Let's hide this. Let's do check-in active document. I know it's about as exciting as watching paint dry, but it is important to make it a habit to rename your features. So let's just tear through and do that real quick. Sometimes it's helpful to roll the tree back. So this would be main housing. I'll go, it's actually main tombstone. How's the music today? Is the music loud enough for everybody? Rear, taper, fillet. I'll call this draft. Fillet. Valve for tuning. Button. Front triangle. This one's going to be called upper sleeve threaded. Oh, we didn't add the threads, huh? I'm not going to add the threads today. Cut for threads. We got our cut for gear pocket. Okay, good. Music is good. Music is perfect. Who's watching TTT on one screen and doing work on the other? Small hole for, I don't know, gear screw? No, for tuning peg. And this is a small hole for wood screw. Larger worm gear sleeve, and then smaller worm gear. sleeve. Okay, that's good. That's a feature tree right there. That's a renamed feature tree. So we did good with that. Let's add some material, and let's check in active document again. So now we've got a version 1 and a version 2 where we've got all those changes. This is going to be the base component in our assembly, but let's move on now and create our second component. This is the one that I've been dreading. 602 button. This is going to be an interesting one, guys. I don't really know how we're going to do this. I've been racking my brain thinking about this, and I just figured I would just start getting in there and creating layout geometry and trying to come up with a plan on the fly. I mean, the overall geometry of this thing is obviously swoopy, lofty. We could certainly, my instinct is just to do it in segments, meaning that I would do a surface loft for this area here, and maybe like some kind of a surface loft over here, and maybe even like a surface loft here for the outside perimeter. That's probably the best way to start, is to do a surface loft, or even actually, I could just do an extruded surface there for that outside perimeter. Maybe this end over here would be a little more tricky, but actually, it almost seems like I'm overthinking this thing. It almost seems like I could just do it with with like a boss wow, this almost looks like I could just get away with doing this with a boss extrude and a cut extrude, believe it or not. I'm gonna start there. Start simple. Don't overwork your brain if you don't need to, and then we'll see if we need to get a little bit more detailed with this thing. But honestly, now that I'm looking at it really closely, I feel like I might have been overthinking this a little bit. New part in inches. Let's go. Top plane, begin a sketch, orient the view, and I'll just draw this thing as it would be in place, meaning that I will just start here at the origin and come over to the side, and this is going to be my shape that comes out here like so, and then comes in like that, and then it'll get mirrored. So let's create some just basic geometry that we can use here to grab some max dimensions off of this thing. Something like that. That's good enough for what we're trying to do here. Make this for construction, and we will hold shift, pick that arc, pick the center point, come across, and we'll say that that's going to have a max distance of 1.306. And then we'll say that the distance from the base to the inside point of tangency, 0.890. And then just to help us kind of keep things in line here, yikes, oh boy, we dropped it. It's underneath the office chair wheel. Looks like about 0.97 to here. Gonna draw another line here to help us make sure we're tangent. And then these are gonna be not for construction because I want to mirror them. So we'll take this and this and this and mirror. And let's see what we can do with our image. So this is another one of these spots where you want to remember that your feature creation order does not create a chronologic dependency. So you're able to do stuff like bring in an image and then use the layout that we just created to size the image, and then you can swap the order, and then you can use the image to drive the layout. So it's kind of a cool little switcheroo. It's 180. Turn off our enable sketch tool, and drag to resize. Again, in the photo editing software, I did make an effort to make sure that these were aligned to vertical horizontal, and you guys have seen me do this enough now that you know how much value you can get from that. You don't have to sit here and futz around with the angle once you bring it into SolidWorks. You can be confident that when you go to bring it into SolidWorks, you're going to be pretty much right on. Wow. That happens sometimes. You don't realize you still have it selected. It's a little hard to see. There's like, I think this is actually the border of the part, but as it wraps around, you catch the reflection. You can see it better on this one. As it wraps around, you catch the reflection. So I think that's pretty good. I think I'm gonna go with that. Let's take that image and make it just a little transparent. This is one where I would have been better off tracing it or maybe using a different color. I tried using black as a background and I tried using white. I probably would have been better off using like an orange or a green for the background. But we'll call this guy image top view, and we will save this model as RBG602 tuner button. And now we can swap the order of this layout from top. Let's do a check in active document real quick here so that we got this thing in the vault. I like this song. And now we can edit the layout and include the, use the geometry from the image to drive the geometry of the layout. So it's kind of cool that you can just kind of swap the order there when you need to in order to get the desired results. So we'll call this one 0.380 for that radius. We can create another radius here. It's almost like just immediately is an arc. So just do that. Like so. Give that thing a dimension. Create our width here at the bottom, which is something that we can measure for sanity check. So our width at the bottom is 0.299. That's pretty darn close. Nice sanity check there, and then we'll make this tangent. And this is going to be tangent here. This can just be merged. These can be swapped back to construction. These can be swapped back to construction. And I think that's pretty much it for our layout from that view. Use a Sharpie. That's good. That's good. I like that. Could use a Sharpie to cover the chrome, take the photo, and then clean it off with acetone. Or just throw it in the trash if you're using a sacrificial part. No, that's a great idea. I like that. I don't know why I made that coincident. It should have been just coincident at the tangency. Coincident at the tangency. Okay, let's exit that sketch. That's our kind of our layout there from that side. Like I said, I'm gonna just try and do this from a point of view of extrude. I don't know if it's gonna work or not, but I'm gonna try it. See what happens. So go mid plane here, and we're gonna take this out to a height of. Let's just again quick sanity check. I mean, it's pretty much 0.26 throughout the entire middle section of this thing, so I think this might work. Very confident, as you can tell. Right plane, begin a sketch, orient the view, and do I have a picture of this thing from the right plane? That's another important question. Did I take any pictures of this thing looking in from the end? I thought I did. Oh, I sure did. Oh yeah, this was the one that I traced. So tools, sketch tools, sketch picture. Oh yeah. Man, if this works, I'm going to be so happy. This is going to be... It's going to let us get into the worm gear and the pinion gear much faster than I originally anticipated. So I'm very much hoping that this will be an acceptable solution. I think it will be. Again, with all this stuff, you have to ask yourself what you're using it for. Like, a lot of times I use this technique to retrofit a 3D print of an invention that I make for something around the house. Or in this case, I'm just doing it to create a cool data set that I can use for tips and tricks this year. So I'll have like a whole new data set that I can use when I'm making tips and tricks videos this year. You know, you have to decide what the application is. If you're machining the parts anew, then it's going to be a much different scenario than if you're using the geometry for the aforementioned reasons. I don't like the way this is popping out so much. Again, we can always account for some of that in terms of like distorted imagery, but it's like way higher than what I was expecting. So again, we're just using this to capture the curvature. We're gonna take some liberties here. Kind of split the difference a little bit there. Okay, I think I'm good with that. And that will be image, side view, drag that up to the top, and we'll go to our right side plane, begin a sketch, orient our view, and we're gonna create I think a lot of times in this spot when you're mirroring, it's just a little bit easier if you give yourself just a little bit of a nub to begin with. So create a little nub there. We could also do this with a spline. That's the other approach that we could use to leave ourselves with all one single surface. So there's certainly an argument to be made on, you know, on either side. But I'm going to just do something like this. And come down. See, did I get coincident to that end? I think I did. Yeah. And then my plan is going to be to mirror this, so I'll create my center line, and let's make sure that our dimension is good there as well. So when we get out to the end, we are at closer to about 0.11. So 0.11. And we can make that a slight angle. Throw in some dimensions here, 0.005. Give ourselves a radius here, 0.75. Give ourselves a nice swooping radius here, 4. And then we will have our, you know, whatever we want this angle to be in this kind of semi-straight section. What's up, the Emerja? Welcome, welcome. Say 5 degrees. Okay, and now we can mirror that. So just window everything here and mirror it. And we can create a vertical line here to connect these two. And we can use our extruded cut, right mouse button through both directions. That essentially does a surface cut. There's an arrow here which says which direction the cut is going. We want the cut to go to the outside. Guys, I think I'm happy with that. I don't think we really need to go too crazy with getting this thing to do what we need it to do. I mean, there's going to be a filleted section here at the end of this part to match up with the geometry looking in from the end. It does get filleted there, so I'm thinking that's going to need to be a variable radius fillet. But if I can just do that, do a variable radius fillet there and be done, I think that's a way better solution than, you know, doing like a crazy surfacey, lofty exercise. Tried today's exercise, but sheet metal is still eluding me. Maybe we'll have to make a solved video for that one. So I'm going to do this as variable radius. Sometimes I'll do a standard radius first just to kind of get myself close to the value that I'm trying to get to. So Like, it looks like about 0.12 is going to get me close. And then I'll go over to variable radius, and I'll take, you know, maybe this point here and start to, you know, pull that down. And then this is going to be 0.02 as well. That looks pretty good. I think straight transition is going to be better in this spot. If you guys are ever wondering what the difference is between straight transition and smooth transition, this is in the property manager for a variable radius fillet. So smooth transition, straight transition. There's an easy way to illustrate that. And that way is you go to a simple rectangular edge of a part and you just try both. So if we did something like this, and then we go radius, or sorry, fillet, and we say variable radius, and we say this is going to be 0.5, and this is going to be 0.125. Well, you can see what's happening here is it's a curvature exercise. So in other words, this starts out with almost horizontal curvature to about there, and then it begins to curve up. That is the result if you use the option for smooth transition. And that's very useful if you're anticipating doing a mirror and you want to, let's say we want to do a mirror here. So I'm going to do a bodies to mirror, and I'm going to mirror this over to this side. You get that nice smooth transition from the fillet. Very, very smooth results. Very nice. It even appears to be tangent because of how I have my view display tangent edges removed, as opposed to tangent edges in Phantom. There you can see any of my tangent edges showing up in Phantom. Now, if we edit that feature, let's roll back before the mirror, and we change that to a straight transition, now you can see it is a linear transition the entire time. So it starts here and it just does a straight transition all the way through. Oops. Straight transition from here all the way through to here. Nice straight transition. So that means that when we go to mirror that feature, there's going to be a hard edge there. See that hard edge? Where that gets mirrored. So that's the difference between straight transition and smooth transition. In the case of this example, it doesn't really make that much of a difference. I mean, it does, it does kind of come off here at first straight and then tapers down. I don't know. They both look good. So I'm happy with either of them. And then you can also see here that we end up with a hard edge here, or a tangent edge, but we end up with an edge here, and we end up with an edge here, and we end up with an edge over here, and we end up with an edge here. So we end up with all these little extra edges, which, depending on what the downstream application is, that can be problematic as well. And what I mean by that is you can end up having a problem with PDM, for example, when you're trying to do mesh, when you have a lot of little edges, because the mesh is going to try to adhere to the edges of your models. So there can be problems with doing that, and the way that you can resolve that is by doing that cut extrude as a surface, as a spline, instead of doing it as a line arc line. So if we were in this cut extrude here and we said edit sketch, and let's get rid of this line arc line, or we could even do a fit spline. Either way, I think I actually would probably prefer to do it with a spline, because then I can make the curvature horizontal at that point. But then we would have one single edge going all the way through, and that would leave us just with one single face. So let's say I'll do it down here. Take this, and this, and I'll do tools, spline tools, fit spline. And then what I'm going to do with that fit spline is I'm going to say that I want to trace over top of the existing geometry, but replace the existing geometry with a spline. Now I've got one single spline here. And so if we look at this cut extrude result, you can see you've got 1, 2, 3, and even a fourth face over here. But if we look at this side here, we just have one single face. And so now if we were to perform a variable radius fillet here, we could use the same, the same constraints, 0.12, And then take this transition point here. I think it was like, I think I did 0.40 and then 0.20. Now you can see that we just have this one single face here. We do still have this extra little face here. That's because of the tangency was coming off and creating the break at that point. But just something to think about. It's a little bit of a nuance, I know, but when you do a fit spline, you have that option to eliminate some of the extra faces. So if those faces are causing problems downstream, particularly with data, what's the word I'm looking for? Simulation, FEA, particularly with FEA, finite element analysis, where you're breaking this up into a bunch of elements and then running, via the mesh process. It can be sometimes problematic to have all those extra faces. Okay, so now I'm going to talk about the mirror all functionality in SolidWorks and the cut in half functionality in SolidWorks. So I'm going to get rid of that extra variable radius I created on the bottom. And the reason I'm getting rid of that is because I'm going to utilize a cut in half function in SolidWorks. And the way that we can do that is we can pick a plane. So here's the top plane, and we can do insert cut with surface. And then you can just pick the direction you want to cut away, and that gives you your cut in half. And then you can start doing your mirrors. So this is going to be a mirror, and you're going to do bodies to mirror. So that's mirror all, top, bottom. And then we're going to pick this face here, mirror, bodies to mirror, and we're going to pick here, and that's going to be your mirror all, side, side. So mirror all, a good bit of functionality to know about when you're working in SolidWorks, and also cut in half. To do a cut in half, all you have to do is select a plane and then do insert cut with surface. And I gotta say, looking in from the end here, that's pretty much what this thing looks like. Like, it's not a circle. It's just like what we're seeing there. It's more like an oval or a slot. So it's very much like what we're seeing here in our SolidWorks model. I'm happy. I hope you guys are happy. If you guys are happy, and if I'm happy, then we are all happy, and that is a good thing. I'm trying to see what the depth of this this hole is, because it is a stepped hole again. So select face, begin a sketch, orient the view, and this is going to be a... Let's show our image from the side view here so we can kind of get an idea of what that hole looks like. So it kind of comes over with a flat... It's just a... I mean, I don't need to see the side view. I know what it looks like. It's just a hole that has an arc on one side and a flat on the other two sides. So I could do something like this, come over with a line, come back, touch the end point, come up with an arc. That's going to give me a perfect line to mirror in a moment. And then all I need to do is measure the opening of that across the flats. 0.1465. And the opening across the arcs, 0.1940. And then I just need to figure out what this arc radius should be, which I'll just measure it to here. Oh, actually, let me mirror it first. If you do something like this, like a measurement to this point, let's say I wanted to put in a measurement there and I wanted it to be 20 thou to that point. When you mirror, you tend to lose that dimension. See that 20 thou just went away? So creating a dimension to a point, well, the reason why is because when the arc is mirrored, it merges and you lose that end point of the arc. So when we mirror this geometry here, the arc is merged and we lose that end point of the arc. And then we have to create those dimensions again. So the dimension across there and the dimension to... Well, essentially, it's the dimension to this point. You're going to have to make that a midpoint relationship in order to lock that down. Or even just a coincident. It doesn't have to be midpoint, but... Okay, that gives us that geometry, and now we can mirror this geometry across. And like I said a moment ago, I'm not really sure what the depth of that thing is. I wonder... what goes in there? This goes in there. I can kind of infer what the depth is from this part. This song makes me want to speed run. 0.47. Not that deep. Okay, and then finally, Hole Wizard on a curved surface. This is kind of a cool bit of functionality to know about. You pre-select the curved surface, and then you go Features Hole Wizard, and we can say this is going to be a countersink, and we can say that it is going to be for a hole with a diameter of some small amount, 0.125. So we could come in here to number 4. Okay, that's good. So number 4 here, and it's going to go up to next. And then when we go to positions, well, now look, we're working on a 3D sketch here. So we're going to drop this thing in here, 3D sketch on a surface. Now we're working in 3D sketch mode, so we want to right mouse button select, and then you can use your planes. You want to always remember you've got your planes in SolidWorks, which are super helpful in 3D sketch mode. So we can say that we want our point here to be coincident to the front plane. So I pick the front plane out the tree, hold control, pick this point, and then we can say that we want that to be on plane. So I pick the front plane from the tree, hold control, pick that point, add the relationship of on plane, and then I'll do the same thing with the other plane to get it to be centered on that model. So just remember, you can use those planes. It's super helpful. So on plane, and then I'll take top plane, hold control, pick that point, and make that on plane as well. So now that point basically has 3 relationships. It's on the curved surface, it's on plane 1, it's on plane 2, and that lets me lock that plane in place. And that is pretty much, I mean, that countersink is a little too large, but that is pretty much what we're looking for. The hole cannot be inserted due to geometry condition. Okay, it's a little, I think it doesn't like that countersink diameter. There we go. That actually looks more like the part too, so happy with that. Remember, if you ever get anything weird like this, when you are doing Hole Wizard holes on a curved surface, you can sometimes end up with abnormal geometry like this. Most of the time, the resolution there is just to do a delete face. So insert face delete, and then you can pick those weird faces. And when you use the option delete and patch, most of the time SolidWorks will clean it up. Oh, didn't like that one, huh? Interesting. Probably because that single point of termination there. Most of the time SolidWorks will clean that up. It didn't do it this time, so I'd have to come up with a different solution, which I'm not going to get into right now. Dang, that thing looks good. That looks just like the main part. Right mouse button, check in active document. Check that in at revision-.02. We can do some renaming here. So this will be main shape from top, cut shape from side, variable fillet, and that's pretty obvious what that is. Cut in half, mirror all. This will be cut for key in worm gear. And then that's the C-sync on the end there. Okay, I think that all looks good. I just want to make this cut for the key a little bit more of nominal dimensions here. So let's make this 0.15, and let's make this 0.2. And the reason I'm doing that is because it'll make it easier for me to size the worm gear itself when I go to put the worm gear shaft together. So right mouse button, plain carbon steel. And again, if you want these things to look good, if you just make a slight adjustment to the appearance, so like if I go in here to the appearance and I make this one out of like a titanium or something where it looks very close to the plain carbon steel but just a little bit different, it tends to make things look a lot more realistic. Or like I can make this one a chromium plate. If the materials are just like slightly different in their shading, then when you go to make an assembly, everything looks it just looks a little bit more realistic. It just looks a little bit better. Emerger says, I got the basic shape, but I can't figure out how to enforce the right value, and thus the weight is completely wrong. Yeah, that one's a little bit tricky, I know. It's the sheet metal one, right? The sheet metal one was the one we did today. The like light mount, I think it's called. All right, 602 is done. 603 is the button screw. I think I'll probably do that one off hours. I don't think you guys need to see me create any more any more hardware. I don't know. It is kind of fun to just add it in the assembly. So file, make assembly from part. I must have done make drawing. File, make assembly from part. And add the tuner housing. Okay. And we're going to add the tuner button as well. And in this scenario, sometimes it's good to have an axis to mount to. So we could go back into this part, once again, use the planes. So we could go front plane and top plane, S key, reference geometry, axis, green check mark, move that up to the top of the tree right under the origin. And we could call this one center axis for mating. And we are going to go to our assembly. And we're going to take that center axis for mating, hold control, pick one of these holes here. I'm going to pick the inside hole that's not tapered, and concentric. Now we got those two mated together. And we just need to get the two washers in place here, which are just going to be a couple of circles. So I'm going to do that in just a minute, guys. I'm going to take a quick bio break. Drank a giant glass of Emergency this morning. So ready for a quick bio break, and then I'll be back, and we're going to keep going today. I don't know if we're going to get this whole tuner done today, but we're definitely going to do a few more parts. So we will be right back and leave you guys with some good music while I'm gone. Hello. Hello. We're back. Sharaith, what's up? Welcome. Thanks for joining us. All right, guys. I'm back. Let me know if I got the music back to the right level. I'm at 40. It's at 40 right now. Got to remember that. 40 is a good number, I think. Might be a little bit too loud. I don't know. Let's see here. Okay. All right. So we got the button in place. We're going to do the button screw. Let's do the button nylon washer and the button lock washer real quick here. So I think I have an earlier picture where I can see that all assembled. Okay, the nylon goes closer to the housing. These are just simple little circles. We could certainly extract these from Toolbox, but then we have to spend time divorcing them from Toolbox. We don't have to spend time divorcing them from Toolbox, but everything works better when they are. So this one is 58 thou thick and 0.192 for the ID. Oh, this is a good song. I hope you guys can hear this. If you guys can't hear this song, you gotta let me know because this is a good one. I like this bass. 0.2865. And we're going to take this out to a height of... Oh yeah, we already got that one. 55 thou. All right, cool. Doesn't like that number. Okay. Material here, we'll make this out of a nylon. And for our appearance, we'll just go with like a kind of like an off-white cream. Music is okay, at least for me. The Emerja says, all right, good. Thank you, Emerja. Appreciate it. Let's save this and let's call this one 605. Button nylon washer. I'm throwing tuner at the beginning of each of these just because it makes it a little easier for me to identify that these components all belong to the same sub-assembly. And this is one of these situations where we do have a cylindrical edge that meets up at the face of... Yeah, I got some more coffee too, Robert. We have a cylindrical edge that meets up at the face of... I'm sorry, we have an edge here, circular edge, which meets up at the face of a cylinder and a plane. And so this is a great opportunity to pick that edge, S key, reference geometry, mate reference, and then just hit the green check mark to give us a default mate reference, and we'll save that part. Let's do a check-in active document to check it into the project. Actually, we don't even have to do that. And then we can go to our assembly that we've been creating. Now look here, we've got an edge that shares a cylinder and a plane. So if we just press the R key and we bring in that nylon washer, you just drop it right in there and it snaps right into place. It's like magic. So you're just bringing this in here, you drop it right in. You don't even have to open the part. It doesn't matter where you select it. You could grab it right from Windows Explorer. You drag and you drop and you let it go, and it mates it into place using two mates. That's kind of the cool thing, is that it actually does that using two mates and they're face-to-face mates. So you can see here that it added in the tree a concentric mate and a coincident mate on these components. So it mated, you know, face-to-face concentric, face-to-face coincident, which is good. That's a strong type of mate. That's what you want. And so just kind of like a cool thing that you can do when you're working in SolidWorks with geometry that has that pre-existing condition. You can save yourself some time and set yourself up for success. And so we can now create our lock washer. So let's save this assembly. This is going to be RBG-6001. Yes, I agree. Tambour station, I completely agree. And this will be tuner. I think I'm going to call this tuner assembly left because we're going to have a right side also. And I don't know if I want to just do it with configurations or if I want to make a totally different assembly. I think I'm going to make a totally different assembly because the housing is going to be different on the left and the right. I didn't really think about that before. But I'm going to make the assembly different. Tuner assembly left, tuner assembly right. So we'll call this one 6001, then we'll have a 6002 for the tuner assembly right. Got to always try and think about these things, think ahead a little bit so that you know when you get to that point of the project, you know what to do. Okay, let's go new. We'll make this one apart in inches. We'll go top plane, begin a sketch, orient the view, and we will create a circle with a diameter of 0.198. And then we will go to features, curves, helix, and spiral. The housing is mirrored, but the gears are not. Yeah, exactly. So it does present a little bit of an issue. We're not going to do like a full mirror of everything. And, you know, there are tools built into the software that'll help you with this challenge. Certainly, we're not the first people who have run into this challenge. And so there are tools in the software that'll help us. But when you're just mirroring certain components, I mean, you know, it's a preference thing too. You got to decide what's going to work best for you. Yeah, I mean, there's always going to be more than one way to do things, and so we just got to kind of decide which way is going to work best for us. I'm going to call this at 0.025 since it is going to be in a little bit of a compressed state, and I'm going to make the revolutions just a little bit smaller. So I'm going to make it like 0.98 for the revolutions. S key, reference geometry, plane. We're going to pick this curve. We're going to pick the end point of the curve. Select face, begin a sketch, orient the view. And we're going to create a rectangle here. We'll pierce the corner of the rectangle to the path. You always want to, your profile should always be pierced to the path. I've got a live presentation coming up here in a few weeks. Tips for sweeps. Be sure to check that out. It is an epic presentation. It's gonna blow your mind as far as what you should do when you're working with sweeps. So keep your eyes peeled for that. I'll get it added to the calendar and everything. But Tips for Sweeps is a very valuable presentation that I'm going to be delivering here in a few weeks, right on this very channel, right here on the live stream. Now, I'm just curious about this. I don't know if it's going to work or not, but I think it is. I think we've done it before. Going to make this 0.317. S key, oh no, surfaces, extrude, and let's put a little sleeve around this thing. Pick on the edge of that surface, S key, mate reference geometry, mate reference, hit the green check mark, and then hide that surface. And I think we did this before, like I said. Gonna make that out of malleable cast iron. I don't think that's what lock washers are made out of. They're probably made out of some kind of spring steel, but I'm gonna make it out of a malleable cast iron just because I think it's cool. Save. Call this one RBG604. And again, this is where it's really helpful to have planned this whole thing out. Button lock washer. So I took all the parts, I dismantled everything, took a photograph, labeled everything. Now it's like I don't need to worry about going out of order. I know everything is gonna work out pretty good here. So we'll save that part, we'll close it. The part's not even open anymore in RAM. We're gonna R key, we're gonna grab that lock washer, move it into place, and oh, no mate reference is showing up. Oh, bummer. I wonder why no mate reference showed up. That's kind of interesting. Let's see. It's just on that edge, it's default. Does it need to be shown maybe? Save, let's return here to our assembly, R key, grab that guy, bring him in. That's interesting. I don't know why the mate reference isn't kicking in here. Oh, we did do this before. I remember why. It's not kicking in because the edge that I selected is not at the intersection of a cylinder and a it's not at the intersection of a cylinder and a plane. So what I would need to do if I wanted to make that mate reference is I would need to pick this edge here, do planar surface, then knit those surfaces together, and then pick that edge that's from the knitted surface and then do reference geometry, mate reference, and then hide that surface. It's a few extra steps. If you're fast with surfaces, it's probably still worth it, honestly, because it just makes it easier to bring this in and mate it as opposed to, yeah, see, now I can just drop that right in there. Boom. That looks beautiful. Question from Tamboror Station. What about an axis? Can we use an axis? Absolutely. So if we came back in here and we got rid of that mate reference, which we can get rid of the mate reference now. It's not going to affect the mate because the mates are to the faces of the surface. So as long as I don't delete the surface, we're good. So then I can pick that axis, S key, reference geometry, mate reference, hit the green check mark, and then I can go to my assembly here, R key, go to drag that in, and when I get over a cylinder, you can see SolidWorks is going to try to mate those together using concentric. And when you do concentric, you can even do lock rotation if you wanted to lock down one more degree of freedom all at once. So now the only thing we'd have to do is mate this into place relative to that other component, and then we would be good to go. So great question. And yes, the answer is yes, you could absolutely do it with an axis as well. Yep, great question. Mate references are just such an awesome time saver because it's just so frequent that you are creating your components in a way that, you know, you're not just bringing it in once, but you're bringing in that same component over and over and over again. And so mate references just totally save you time in that arena. So what I did there was I dragged that tuner until it was almost touching with this lock washer. We could even, if we wanted to emulate compression, we could, we could just adjust that helix if we wanted to emulate compression. So the dimension that I took for that helix height was at a open non-compressed position. So if I made this 0.015, now it's going to be a little more compressed, and now we see why it was important that I left a little gap there at the end of the helix. We could probably go a little bit 0.99 and still have that little gap. But then once you feel good about that, sorry, I try to hide the geometry on the way out. Once you feel good about that, then you can move this until it's almost touching. Certainly you could use interference detection or collision detection if you wanted to. So I could do a move component here and I could say collision detection. And then when it hits that other part, it stops moving. Now I can hit the green check mark to finish that, and then I can pick this face, hold control, pick this face, let go of control, distance mate, and SolidWorks is going to tell me what the current distance is. So I'll just leave it at that. Boom. Now I got that distance mate in there. And then as far as rotation goes, it's up to you guys if you want to lock down the rotation. Most of the time I do, and most of the time I just do it with a parallel mate. I know you've got that lock rotation option, but at that point it's kind of like, why even bother locking it down? But I will say this. Robert making a great point here. Yep, we could definitely do that. That's a great point. So Robert in the chat is saying, why not make a configuration where it's compressed flat and a configuration where it's open? That's a great point. And so the easiest way to make a configuration in that scenario is to get the dimension for the height to show up. So let's see here. I don't know which one is the height. Well, let's just change one. Okay, it's that one. So the easiest way to make these two configurations here would be to take this dimension here for your height, right mouse button, and say configure dimension. And once you say configure dimension, you can make one here that's called uncompressed. And then you can make that one 0.035. And that's going to create a new configuration in your tree. I didn't mean to have that extra character on the end. Uncompressed. So that's going to create a new configuration in your tree. So you've got a configuration here called default and a configuration called uncompressed. So you just find the dimension that you want to change and you right mouse button on that dimension and you say configure dimension. That brings up this table, and then you can make the dimension different for your different configurations. I think that was the wrong dimension there. So now we've got a compressed and an uncompressed version. Excellent suggestion, Robert. I love it. And let's rename these features real quick. I mean, really, we don't need to, but this is sleeve for mates, plain for mates, knit for mates. And we do need to leave that surface in the tree. We can hide it, but we can't delete it because we do want to mate to those surfaces because it's just way easier. But certainly there were other ways we could do it. We could mate to the axis, and then we could put like a distance mate into the origin, or to one of the planes. So check in active document. I don't think we're going to change this part anymore, so I will release ownership. Check that thing in. Revision -.01. Happy with that. And we're happy with how this thing is looking. Again, we could get in here and add some additional mates if we wanted to kind of lock things down. So front plane of that, parallel. It's easy enough to do. You just kind of look for your locations in the tree where you've got a minus sign, which indicates that the component is able to turn. This one I might actually do with an angle mate, and the reason I would say that is because then that lets me create different configurations. So I could have like a right lower and a right upper with 2 configurations where the angle's a little different, and that will look good when you do rendering. So I might do an edit feature here and change this to an angle of 0, and then I could create a configuration of this assembly at angle 1 and at angle 2. So I'll rename that one here, or actually I'll just make new configurations later once I have everything in place. And then the tuner button, which I'm going to reorder in the tree. So it's 602, 604, 605. And we will see there's a minus sign there. So we'll go front plane, hold control, front plane, make those parallel. And now all of our components are locked in place. Let's go into our vault here and do a check in active document. I wonder if I can just right mouse button anywhere, or if it'll put that in standard docs. Okay, cool. It is putting in the right spot. So it's always good to keep an eye on the location where it's getting checked into. If you just do kind of like a generic check-in, it might put it in your top level folder of the vault or of your data management system. So it's always good just to do a double check, make sure it's going into the right spot. You'll notice this component here, the lock washer, is not being checked in. Why not? Because I released ownership, which means I'm not changing anything else with it. So don't bump that one up to the next level. We don't need it. But the rest of these are going in, and they're going into the correct spot. That's what we want. All right. Let's see if we can get this hardware to just auto-populate here. So that'll save us some time in creating that hardware. Looks pretty good. Looks like it's getting more or less the correct size. No matching size, huh? Well, that looks pretty much like it's matching. And then for the length of that, we can make that length... where is that screw? This one. .63. We'll call it 0.65. Okay, done. Another component done. Of course, I'll go in here later and divorce that from Toolbox and put in the correct information, but this is looking pretty good. Let's get on with it here. Let's go on to the next component. Oh, good. The worm drive shaft. This will be a fun one. So we've got the worm drive shaft here on the desk. We are going to take this, this is all rinse and repeat, essentially. We're doing the same things over and over and over again here. So we will create the geometry for this. We will create, the cut for that worm gear using the image to help guide our process, and start out with a new part. And once we make this new part, we're going to go to, I'm just kind of keeping everything in the same orientation it's going to be assembled in. I know it's a little bit different from the normal orientation that I would use for this type of geometry, but this is the orientation that it would be assembled in, so that's what I'm going to go with here. So this will be, it's kind of like a line that comes up and over and then down to where the worm gear itself is, and then it looks like it's about the same diameter. If I just roll it on the table, it's about the same diameter there. Comes over, down, and then it goes into a final section of diameter, which does have a little notch in it. But that should give us a pretty good start for our layout geometry. Make sure we zero this out. Okay. So we got 0.2750. And then that gets to the point of the worm gear at about 0.187. And then the length of that worm gear section, call it, this isn't like a critical dimension here, but we'll call that 0.36. And then the overall length of this 0.86. I wish I had a white keyboard. It'd probably be easier to see some of these parts for you guys. Tell you what, if I sell 1,000 t-shirts, I'll buy a white keyboard, so it'll be easier for everybody to see. I think this is the same diameter. Yep. So I'll just make that the same, and I will right mouse button, make that driven. And then I'll pick this guy and make those collinear. And our final diameter, 0.1875. Nice. And then our overall length of this thing is 1.712. Okay, and we're going to call that our layout from top. And we are going to right mouse button, sketch color, make that something that really pops out. And now we are going to top plane, begin a sketch, orient our view, tools, sketch picture. And let's get that worm gear. I think I like this one more. I think this one's a cleaner picture. I'll make this 90 degrees. And let's see if we can get that to size. Size down, as they say in poker. See, in this spot, a lot of times it's good in the layout to mirror the layout. So we take all this and we mirror it. And that way, when we're trying to drop this image in, it's a lot easier to center it. If you only have the one half, then you're kind of like, am I centered or not? I don't know if I got this right. But now that we have both, it's a lot easier to definitively get this centered. It's kind of hard to tell where the worm gear begins, so I'm just going to base this on more of the overall length. That looks good, right? That's it. It was a lot easier than I thought it was going to be. Let's take the transparency and just bump the transparency a little bit. Okay. And we'll go top plane, begin a sketch, orient the view, and capture this main shape here, which will be these. Convert, trim. Remember, trim you can use to trim, but you can also use it to extend. So trimming some of these entities, extending the others. Features, revolve, and that is our main shape. And Control S for save, and we'll call this 606 tuner worm drive shaft. And then we can go top plane. See, this is where again we have to decide kind of how detailed we really want to get with this thing. I mean, this is really like a variable radius helix to get the concept down, where the radius starts out outside of the model and then tapers in and then comes back outside again. So what I'm saying is, if we were to create a, if our goal was going to be to have the worm gear start right where that, right where this green line is here, we might want to start out with our sketch plane for the helix a little bit before that. So let's say we make that like 0.125, just a little before, because it's going to start out with a sketch that's larger than the geometry of the overall worm gear shaft. So, we could create some kind of a larger, let's say 0.35. Yeah, maybe even a little bit tighter than that, like 0.3. And then we can use that to, I almost feel like making that relative to the edge of the model, because it doesn't even really need to be that much bigger. Like maybe 10 thou would be enough. That was pretty close. Okay. 10 thou per side extra. And then we go here to curve helix spiral, and we would use this variable pitch option. So with the variable pitch option, what we're able to do is we're able to say that we want this to go, let's get the picture shown here so we can really follow the picture. So we're going to reverse the direction on this thing, and we're going to say that we want this to be, what are we doing here? Height and revolution. So we can say that we want this to be at a height of 0. Let's say 0.06, okay, to kind of get us started. And then we can go to a height of 0.12. So I'm essentially using 60 thou as my pitch, really. I'm thinking this should be height and pitch. Yeah, that's better. You can measure the physical part here to get the pitch on this thing. It's actually closer to 80 thou for the pitch. We'll make this one here 0.80. But what's going to change in this transitionary period here is going to be the diameter. So the diameter is going to come in and get tighter. Down to about, call it 0.1875 for the diameter there. So the diameter is going to be at 0.295, and then it's going to pull down here to 0.1875, and it's going to stay at that 0.1875 as we create these additional sections of the helix. So this will go to about 0.32 and 0.08 and 0.1875. See, it's going to go, let's see here, 1. That looks pretty good. That's actually holding pretty tight to what we had there. The only difference maybe would be that I'd make this like 0.4. Kind of split the difference there. That's pretty good. And then after that, we can start using that distance of 60 thou again. So this will be 0.44, 0.08, but now the diameter is going to go back out to that 0.295, and then 0.50, 0.08, and the diameter is going to go out to that 0.295. So that should leave us with our helix here that we want for this shape, and then it's just a matter of going to that helix, select a S key reference geometry plane, select that curve, select the end point of the curve. That's going to be our sketch plane for the cut for this worm gear, and that cut is going to be our tapered shape, which is basically this shape here. So we'll go, we can kind of just eyeball this up here, do a shape like this. And again, if you want to really learn about how to properly create this type of geometry, you can look up Jeremy Regnerez, and his content is phenomenal on this topic. He's a true pro, and he'll definitely help you if you need any legit gear design. This is kind of like amateur gear design that we're doing here. Fortunately, we're not machining this, so we can get away with it. All right, and then you can kind of figure out where that would be cutting in. Where that would be cutting in, and I'd say it's going to be cutting in over here, and I'll probably put it. Looks like I kind of picked up that gear on more so on the edge of the helix there, so maybe I would do something a little bit more like that for the cut. And then we can exit sketch, and we can do swept cut and sweep this profile along this path and see what it ends up looking like. Failed. I think I'm too close here. Let's go. 0.05. Kind of got to figure out what this distance is from here to here. 0.04. And then I could probably make this just a little bit smaller. So it's failing, and it's probably failing because of this distance here being too close. Bottom of gear circular. You're saying this face here, this edge here should be circular? I can fix that. Let me just see if I can get it cut to look good. Yeah, I'm also a little hesitant to make it circular just because of the triangle count issue. So I know what you're saying, Robert, and I agree with you. I also just want to see if I can get this thing to work at all. What the heck's going on? Why am I getting no... It's because that pitch is spiral. Yeah, okay. I'm just going to go a little extreme here. I think maybe I made the spiral pitch too narrow here. I'm just looking at it, giving it another look here. Looks like these are very close to one another. Okay. See, sometimes if you just keep dialing it down until you get a preview, it can help you figure out what's not working. Let's go back to our Zoom previous. One of the best tips that we've done in this this thing so far. So this is what I wanted here. I'm happy with that, but obviously it needs to be a wider angle. Okay, gave me 0.03. I feel like I have a little too much. 1, 2, 3. No, that's what I want. 1, 2, 3, 4. Well, 1, 2. It would only be 3 valleys, right? So maybe my pitch. I think it's going to be my pitch that's going to need to change here. So 0.125. Going to go just a little bit bigger with the pitch here. Probably a little too much. I'm using tab with my left hand there. Tab through this. 1, 2, 3. 1, 2, 3. Okay, yeah, that's. I like that better. That looks better to me. And then let's see if that gives us the flexibility we need for this. Make that a little bigger. Okay, yeah, there you go. That looks a lot better. Still want that to be. Wonder if it'll let me get away with this. Ah, there. That looks pretty close. So it looks like maybe my pitch is still a little off, but I think that's pretty close to what we wanted here. I wonder if I can go just a little. Honestly, I wonder if maybe it'll be different if I did that pierce at the other location, like did the pierce centered instead of doing it how I did it there. Especially now with me changing the pitch. I also think there's a little bit of a misinterpretation of horizontal vertical when you do this, because it's not It shouldn't be really true horizontal. It should be a little bit on an angle here for this. But again, we're kind of in that space between illustrative and reality. So I just wanted to look. I'm taking my time on this one because I want when I mesh the gears together, I want it to look, you know, fairly clean. Just as a personal challenge, you know, just doing this for me and for you guys, of course. Let's just look at this as a solid here and just make sure that we're going the wrong direction. We got the helix going in the wrong direction, which may also explain why I'm getting some abnormalities from the. There we go. That looks much better from when I'm comparing it to the view. So it looks like we've got still have just a minor issue with the pitch. And I think that once we get that down, we're going to be good. Let's go 0.085. Now, another way that you could do this as kind of an iterative process would be to do it as a constant radius pitch. Make the gear first and import its picture map for the depths. Oh, that's good. I like that. Yeah. Yeah, so another way that you could do this would be to do it as a constant radius helix and just kind of like get it to look good in the area where the gearing is taking place. And then you could come back and you could do it as a variable radius. But I'm going to say that that's pretty good for now. That definitely looks like the worm gear. So this will be the main worm thread. And this will be the sweep cut profile sketch. And this will be the helix sketch plane. This is a plane. And this is the image on top. And we can hide those. And we can hide that extra sketch plane. And we can set this to a material here. And we can adjust the color of this thing. This has got a little bit of a darker color. We'll do this out of a metal. And let's go magnesium. Yeah, that looks good. And then we'll hit the little beach ball up at the top and just make that a darker color. And save. And let's do check an active document. Looks good. Worm gear, check that in. And then we have a just a couple more features on this thing. So if we show the image again, you can see that we've got a flat spot here. So we'll go top plane, begin a sketch, orient the view. And this is going to be a center line. And then we're going to do line that comes across like so. And that's going to have a width here of... Man, I got way too many parts on my desk already. 0.139. And this angle here is, yes, 45 degrees. Perfect. And then the distance from the tip to that angled area is about 0.435. Whoops, that doesn't look right. Is it really that far off? It's more like 0.446. Okay, it's good. And then features extrude cut through all in both directions. This is going to be the side to cut. That removes it from our solid, and then we can mirror that. So that's our solid there. We can take that and we can mirror it. Here's another kind of cool trick in SolidWorks is when you're working in SolidWorks, I'll call this flat spot 1. When you're working in SolidWorks and you do the same command over and over again, so like if I pick the flat spot 1 and then I hold control and I pick the front plane because I want to mirror about that and I let go of control, you get this, it's called a context menu. So this is, in this case, if I go flat spot 1, hold control, pick front plane, let go, this is the context menu here. You can right mouse button and you can choose to customize that context menu. And so now from here, what I could do is I could go to my features commands and I could drag and drop mirror onto that menu. And so I can say, okay. And so now anytime I pick this and hold control and pick the front plane and let go of control, mirror is just sitting right there waiting for me. You guys have probably noticed that I have that enabled in sketch mode for sketch mirror, but we can also do it at feature mode for feature mirror. Good solid shortcut there, customizing that. It's called the context menu. Flat spot mirror. If you guys like that one, be sure to like this live stream. And then this thing has a tap hole in the end for this screw that we are bringing in from the button. So it's got a tap of about 90 thou. So we can pick this face. We can do hole wizard. We could do hole type and make this. I'm just gonna make it a regular hole. I'm not gonna make it a. I'm not gonna actually add the cosmetic threads. And then for the depth of that, that's gonna be blind, and it's gonna go to. It doesn't need to go that deep because it's going through. Just gonna make it a 1/4 inch. That is gonna be a tapped hole, but I don't like it when the cosmetic threads show up everywhere. Annotation wise, so I'll save the cosmetic threads on that one for later. So that's a worm gear. Oops, let's turn off the shadows. That looks like a worm gear to me. It's spinning. Don't know why it's spinning off center, but like, like the center's just going up and down. Oh, probably because of this. Yeah, I have that extra sketch there. Okay, so we'll save that. We'll do check in active document. And this is going to, ideally, it's going to abut right to the edge of the housing. So I'm going to take this edge here and make that my reference geometry mate reference. That's what goes right into the housing. And then I'll close that part. And then here I will R key to bring up that part and drag and drop it into place here. And then I'll just press tab to have it flip the other direction. And that's where it's supposed to go. It's supposed to go right in that hole. The question is, what happens when we look at this thing in a section view? And the answer to that question is... planer. Oh, good. Yeah, that's what I wanted. It's perfect. That is perfect. That is wow. That is exactly what we were hoping for. That's exactly how it would go in. You can even see on this little screw here the engagement. You can see the thread engagement. I'm gonna use the Robert trick, getting my head out of the view. Maybe. I'm really pushing my webcam to see how it does with focus. Well, there you go. Oh, we got it. So you can see the thread engagement. It's like a discolored section at the front of this thing. Come on. Nope. All right. It's perfect. Trust me, guys. It's perfect. What we got here is perfect. So, where does that leave us? Well, it leaves us at the point where we're ready to do a check in active document. That's for sure. So Control Q, Control S, right mouse button, check in active document, and everything is going into the correct project. We'll do a check in. Very happy with that. And so now it is time for the, what should we do next? I guess we should do the Pinion Gear next, right? Those two go together. So we can do the pinion gear next, and I'm thinking that's probably going to be a good stopping point for today. We're going on here almost 2 hours. I would love to do this whole thing before we break for the weekend, but I don't want anybody to get too burned out as we're going through here. So let's do the pinion gear, and then we will, well, we'll see how it goes. I mean, if we're feeling sassy, maybe we'll keep going. Did I get the little pocket for the cover? I don't think I did. I sure didn't. I gotta get that pocket. $0.596. And maybe I should just make that 0.60 since the thing's going to sit in it. And then that's going to go down to 0.035. Okay. Missed it. Sorry, guys. Oh, yeah, that looked much better. This thing looks awesome, man. Wow. All right, cool. So let's go to new, part in inches. We'll go probably front plane on this one. Let me look at the assembly again. It's gonna go right in through the bottom here. Have a screw hooked in on the bottom, so yeah, I think front plane. And then this one is going to be just gonna do the full diameter with the screw threads all at once. So 0.505. 0.505 over 2, because we're putting in the correct thickness there. And then this is going to be 0.1395, really like 0.14, and this is going to come in and over and close, and our total height here is going to be 0.2015, and then our diameter here is going to be 0.3265. 0.3265 over 2. Sometimes I just don't have the center line in there, right, for my dimensions, so you just got to deal with it. I wonder if you can reattach and then like swap it out with a diameter dimension. So if I reattach this here, oh, it just auto swapped. How cool is that? So I'm clicking on the dimension, grabbing the endpoint, then dragging it onto the center line, and then it just like auto swaps it to a diameter dimension. How cool is that? The answer is very cool. Top plane, begin a sketch, orient my view, tools, sketch, picture. And we will grab the gear here, looking down from the top. And resize it. And then we can do view and wireframe so that we can see the circle. So this is a different approach. Instead of doing this as a layout where we have the sketch where we can change the color, we're doing this one just right off of the geometry that we made. We just made the geometry first. Now we're dropping in the image so that we can use the image to help drive our design. So trying to show you guys some different techniques. You probably don't want to be bouncing around using every single technique when you're actually working with a team. You want to be a little more consistent, but when you're demonstrating for the crew, it's good to show some different techniques. Okay, that's nice. Gives us a nice top view looking down on this thing. So now we can go top plane, begin to sketch, orient our view, and we can create the sketch here for the little cutaway. This is for construction. This is vertical. This is mirrored. This is mirrored, but not this, because you only want one line in there when you're doing the mirror. Give ourselves a radius here and hold shift, and we can go end to end here. And that gear is going into this thing. Yes. That gives us some nice, easy to measure geometry. So 0.195, 0.230. S key extrude cut, and that's going to go through all. A cut. And could probably actually come back before that. Image, gear, top gear. And then we could go here to the side, front plane, begin a sketch, orient the view, tools, sketch picture. Bring in this image here. -90 instead of 90. This part's not threaded, is it? No, those are just texture images. I know I'm going to have to cut revolve a little bit around the outside of this thing to clean it up, kind of chamfer it a little bit, but mainly I'm just trying to get the idea of this path right here. Alrighty, and now we can go to this plane here, select face, begin a sketch, orient the view, and we can do a convert entities, and we can go to features, curves, helix, and spiral, and then we can go to our front here, and we can say that we want that to be constant pitch, and that we want the height to be whatever the height was of the gear. Maybe it could be a smidge more, but so height and pitch. So this could be 0.14 or 0.15, and then the pitch. Actually, this could be height and revolution. We did this earlier in the project too, where we made this like 0.125 just to see what it looked like. And then for our start angle, we want that start angle to be something on the front here. So make that 90. There we go. That's on the front. And then say 0.04. Okay. Control A, 0.02. Enter. Control A, 0.01. Enter. That's pretty close. Control A, 0.09. 09. That's pretty good. Pretty right on that one. So we can hit the green check mark there, and then we can do very similar to what we did in previous examples here. We could pick this face, S key, reference geometry, plane. Pick the endpoint of that helix, and then we could pick that surface, begin a sketch, orient our view, and then we could try to capture what's going on with the gear here, as far as the the cut down in there. So that might look something like, I'm just going to do this very simple. Something like this. Don't want that to be vertical, but Might be something like that. We could say that this is going to be some symmetry here. This symmetric. And then we can control that radius, and we can control the angle here between these two. Whoops, 0.29, no, 29. Yeah. And then as far as this angle goes for this first one, you know, we're gonna have to decide where that first, you know, gear is going to go. I mean, it really should be aligned with the rest of this thing. So I could maybe move this helix over now that I use the front plane to determine the location of the helix. I could do something like bring this out a little bit more and then create a connector between these two. Let's say we'll make this perpendicular. And we'll make that coincident as well. This is looking down from the top, right? Why did it move way over there? Interesting. Okay. And so then we can maybe locate this. That's probably okay there, actually. You know, something like this. And then we can take that helix from the previous step and we can adjust the start angle here so that it's more centered on that tooth that we're working from. Can drop this in here like this. Could even use like a fix relationship at this point if you wanted to lock everything in. And now we're ready to do our sweep cut. So we go here to sweep cut, sweep this curve, this profile along this path. Like so. That gives us 1. And then if we return to the top view, we can use the circular pattern function to give ourselves a circular pattern of those teeth and to save ourselves the problem of counting teeth. So we could just we can just use the image here. So looks like I got them all, right? Oh yeah, first try. And then we would have the challenge of getting the fillet on here on the outside of this thing. Well, we might be able to resolve that challenge by using the SolidWorks functionality for auto selecting, since these are all kind of coming together at the same edge. So if I was to figure out what that radius is supposed to be and then pick one of these edges, I can use this option here to get all the edges that are connected. And then that gives us the fillet there as well. So view, display, tangent edges removed. Yeah, I like that. Like I said, I might want to go in here and go front plane, begin to sketch, orient the view, and create center line like so, and create something like this. And then mirror that. So in this spot, what I could do is I could just drop a mirror line out here in space and then mirror this geometry and then take this and make it collinear to this lower edge of the model. And that'll center them so that they'll, you know, it'll be properly symmetric. Take a measurement here. More, okay, there you go. Kind of split the difference. And what else is open here? This guy's open still. So I'd want that to be the same as this earlier sketch from the main revolve. Ah, it's over on the other side. Do something like this, right? Take that and make it midpoint. And then make that coincident, or even a little bit further out. And then take this line here, we'll hide this, and take this line here and features revolved cut. 0 thickness. Okay, so this coincident that I added at the end there should probably be a slight distance. And then this center line, revolved cut. There's a 0 thickness somewhere else that it doesn't like, huh? Let's figure this out here. So if we take maybe we'll get rid of this. Just trying to create a little bit of a gap on this thing before it revolves around. Whoa, what the heck? What's going on there? Maybe that's part of the problem too. That might do it. Okay, there we go. That's what we wanted. All right. And so now that we've got all this geometry in here, we can assign a material. This looks like it's some kind of a brass. Okay. Oh, there we go. Copper alloy. Okay. I don't really like that color too much. That's better. And we'll save this. And this is going to be RBG 607 Pinion Gear. And let's check in active document. See, now here it's not going into the correct project. So I want to make sure that that's going into the correct project. That's a common thing to look out for in a data management system. There we go. Now it's going into the correct project. And we could mate reference this thing, but I think I'm just going to drag and drop it in. So Control Tab back to my assembly, and we'll do an R key for recently accessed documents. Drag and drop that in. Oh, you know what? This has one more feature on the bottom. It's got essentially it's a countersink to make clearance for the screw that goes in there. So let's add this one last feature here. Can really just go up to a peak. So I was able to hold shift there to go across the center line and get a double dimension for an angle dimension when you're doing a revolve. Another good trick to know. So I got a double dimension there for the revolve angle. And then this is going to be at a depth of something very small. I'll say 30 thou. And it's going to be at a diameter of 0.3125. And that's going to be features revolved cut. And there we go. Yes, that looks like what the actual part looks like. Yes, much better. And so now this is going to be concentric to this. Make that concentric. And then how does that mount up in there? It goes. Let's see. Looks like it just kind of goes up against that hole that's in the bottom of the main part. It doesn't like seat in there or anything. So this just mounts right up against that hole. And so the worm gear turns and it will turn this part, hopefully. That's the idea here, right? So if we did a gear here, the good news is they do look like they're engaging at the right angle. Looks like my thicknesses are a little bit off, but certainly looks like it's going to be close. Maybe a little bit of a refinement on my worm gear part there. But if we do our thickness, our mate here, and this is going to be a mate between a mechanical mate, and I usually just do this as a gear mate. So the gear mate would be between this surface and this surface. So basically what that'll do is when one surface spins, the other one will spin. And you can immediately test this. So as soon as you apply it, you can test it. You can begin moving your components and seeing, if you're close to the correct ratio. And then what you can do is you can start to refine that. So let's just say we make this 1:32. And looks like that is a reverse. And then you can just keep refining it until you get to, the correct amount. Of course, there's obviously a way to more elegantly figure this out. But this is something that, you can definitely use something like this technique like this to get yourself close. And really what we should be doing here is this component here, the tuner button should have a mate for angle. And then this component, the tuner worm gear, should have a mate for parallel to the tuner button, so that when we turn this, it drives that gear. Yeah, I mean the gear mate Tambora station, it's really simple. It just says that for every one rotation of this surface, cylindrical surface, this surface will rotate X number of times, or vice versa. So in this case, it's this one rotates 1 and that one rotates 52 or whatever it is. In this case, it's going the other way. This one has to rotate however many times in order to get this one to rotate 1. But that's how the gear mate works. So I think that's pretty good. I think we got ourselves pretty close here. The motion certainly looks correct. When that thing is in the housing, people aren't going to see the engagement. Not that that's the point. It's not the point of what people will see or what they won't see, but it will look pretty slick. And I'll do some refinement over the weekend, and I'll get that gear mate really working in there pretty tight. But we're going on over 2 hours now, 2 hours and 20 minutes. So I think this is a good place to stop. I think that we really accomplished a lot here as far as getting ourselves into a good spot for for the gear mate and setting ourselves up for success for next week. So let's do a check-in active document here, get everything to check into the vault here. We have our one piece of hardware, our flathead screw that we really we don't need. We need to replace that with a proper, a proper component. But this was awesome, guys. I think we did really good today. This is definitely going to make for a great component to add to the overall bass guitar. And we don't really have that many more components to do here for this one. We just have the tuning post, which is a revolve and a little slot in the middle here. And we have the Pinion Gear screw. Just grab that out of the toolbox. We have the Pinion Gear cover. That's a puck. Very, very simple to create that. And then we have the hex bushing, the bushing washer, and the mounting screw down at the bottom here. And then we're done. That's it for the tuner. So this is pretty cool stuff. I want to, as always, thank you guys so much for joining me today. I think we were able to really accomplish a lot, and I'm glad that we were able to accomplish it together. And if you guys have any questions, feel free to put them in the chat or put them in the comments down below. Don't forget to like, subscribe, and buy a very soft TooTallToby t-shirt. And I will see you guys on Tuesday next week. I'm also planning on doing Model Monday live on Monday night. So if you're around on Monday night, you want to hang out, do some challenges, some speed modeling challenges, let us know. But yeah, this is pretty cool. Tambour Station, I agree. There's lots of parts to create in this thing. And this one surprised me when I started taking it apart. I was like, oh man, I forgot how much was going on in this thing. But we made some great progress today. We got through a lot of the pieces. We got ourselves in a good spot to finish this up on Monday. And then on Tuesday, we can really start focusing on doing the strings. And that's going to be it. I mean, the strings are the finale of this whole experiment. So hope you guys enjoyed it. Let me know in the comments what you liked, what you didn't like. Let me know if you have any questions, and I will see you guys hopefully on Monday night, but I'll definitely see you on Tuesday morning, 9:30, where we will continue with this live stream modeling of the bass guitar. Have a good Friday tomorrow. Have a good Monday morning. Friday and Monday are great days to hustle. So make sure you hustle, get yourself set up for the weekend, and of course, have an awesome weekend. See you guys next week.